Okay. Yeah. So as Yashi mentioned, I'm going to talk about AI HPC applications, performance, and scalability. This is kind of from the paper presented at IPDPS this year. So as you can see, there are a lot of names here, right? So this work was done by my talented colleagues. So Colleen, Umesh, Ricardo, Khalid. I think Khalid is here, right? So, and the Yashi team, Abhishek, Mati, and Vino, Archit, and John and Scott. So most of them are application point of contact. So they practiced the performance and scalability test on the three different systems. And Colin and I also the application point of contact on Colin and me and Scott. We got all the data from each owners and analyze process to give you the snapshot of our test. Okay. Okay, so I'm going to talk about systems and application overview. So first of all, systems. We use three different systems. Aurora, we have Aurora, exascale system. Frontier, another exascale system managed by OLCF, which has AMD GPUs. Aurora has the Intel GPUs. And the third one is Polaris, which is another AirSAP system, Parascale system, which had A100 GPU. Do you feel this echo here? It's okay. It's okay. Yeah. So again, we have three different systems with the three different GPU vendors: Intel, AMD, and NVIDIA. At the left bottom, you can see the table, quick summary of the system. Aurora Frontier exascale system, it has around 10,000 compute node. Polaris is Parascale system, around 500 node. And Aurora has a dual circuit CPU and 6 Intel GPUs. And Frontier Polaris has a single AMD CPU with a 4 GPU card from AMD and NVIDIA. Aurora has 1 terabyte in DRAM on a node with 8 NICs, so 200 gigabyte per second in the memory bandwidth. And Frontier and Polaris has half terabyte DRAM, and Frontier has 4 NICs per node, and Polaris is 2 NICs per node. This table shows, sorry about too many numbers, but this shows some comparison between the GPUs on Aurora, Frontier, Polaris, and node level. So if you look at the GPU part, Aurora Frontier GPUs, compute peak is around 40 to 50 teraflop per second because they have same generation from different vendors. And HBM capacity is 120 gigabyte, and the TDP is 500. So if you just check the peak performance of Aurora and Frontier GPUs, the theoretical peaks are pretty similar to each other. Polaris is one generation earlier than the other system, so its compute peak is 20 in single precision, 10 in the double precision, and HBM capacity is 40 gigabyte, pretty smaller than the other system, and TDP is 400 watt. So in this study, there may be several configurations, but for compare the performance, what we did was we assigned the same size of workload per GPU card. They may be not best for the Intel and AMD GPUs because Intel and AMD GPUs has some more compute resource, more memory, right? But you just use that configuration. So NVIDIA GPU has better chance to get the better GPU occupancy and better performance in this configuration, for your information. So if you look at the node level comparison, Aurora has 6 GPU per node, while the other Frontier and Polaris has 4 GPU per node. So because of these two more GPUs, node performance of Aurora is better than Frontier in terms of compute peak and the memory bandwidth, and also HBM capacity is 50% more and higher NIC bandwidth. And the slingshot fabrics are same, right? And then we are interested in seeing the application performance. So when we started developing Aurora, we have a lot of mini apps, benchmarks, HPL. Those data are very, very important to understand the basic characteristic, but we are a facility to support our user groups, right? So we want to know what is actual application performance? So we chose 12 HPC AI applications to represent our various science domain. So you can see we have some modeling application, CFD, electronic structure, material science, and plasma physics and particle transport. And also even for the ML side, we include AI application, GNN application, and large language model and chemical ML applications. And as you can see, they have a different base language. We have 6 applications written in C++, 2 applications written in Fortran, 4 applications written in Python. And they have their own choices of the portability layers. Some of them use OpenMP offloading model, OpenACC, or Cocos Oka framework, MREX, TAM, or PyTorch or TensorFlow for the ML applications. So on the right-hand side, you can see all the different characteristics of applications. So we just want to cover the variety, the various, the scope of the applications in this test. In general, we try to do the weak scaling approach, but some application like games and NWChemX, by the nature of the algorithm, it's very hard to configure for the weak scaling. So for these 2 applications, we use the strong scaling, which means we have the fixed size of problem, and then we just increase number of nodes. And just out of curiosity, for FlashX application, we use both of them. So we do the weak scaling test and strong scaling test and see the difference. Okay. Yeah, another big table. We just want to categorize what is the algorithm motif of each applications, what is the performance characteristic. So most application we use double precision, and the SimAI bench and Cosmic Tagger we use a single precision, and Megatron disk speed we use half precision. And for the third column, you can see a lot of different algorithm motifs. So by the nature of the application, there are so many myriad of the kernels launching for the workload, right? So it's not easy to say this is only used this algorithm. Each kernel have their own algorithm, different performance characteristics. Some of them may be memory bandwidth bound, some of them compute peak bound, maybe network latency bound, etc. Right? So it's very hard. This is main difference between the micro benchmark versus applications. Application has so many different jobs, so many different kernels, different characteristics. Okay, so that's kind of overview of applications and the systems, and then let's move on the performance. So in this slide, so as I mentioned before, in this study, we tried to use the same workload per GPU card. And then that is a little bit beneficial to the NVIDIA GPU, but that's what we tried. So same size of problem solving the same GPU card, right? In this slide, x-axis shows application names. You can see all the different application names. And y-axis shows the speed up over A100, which means your bar is higher than 1.0. That means your application perform better than A100. Lower than that, slower than A100. And you have each application of 3 different color bar. So green, NVIDIA, and black, AMD, and blue, Intel. And each bar has some labels, right? Those numbers represent a figure of merit. So for AML Wind applications, NVIDIA 25 means 25 million cells per second for a single time step. AMD 33 million cells per second, and Intel 26 million cells per second, something like that. So based on the application, they have a different figure of merit definition, and based on that definition, they measure the performance. So in this case, we use a single A100 GPU, 2 GCD of MI250X because 2 GCD is in the same card, and 2 stacks of Intel Max GPUs. So as you can see here, MI250X performed best with the 5 applications, AML Wind, Games, XGC, NWKMX, and FlashX. And the Intel Max GPU operate best with the other 5 applications, CNS, SimAI, Cosmic Tagger, SST, and OpenMC. For your information, this is what we measure, but it doesn't mean it represents all the the performance of application. Depending on the workload and the problem size, you may see some difference, but at least you can see some trend here. Okay. And then we did scale up on the node with the multiple GPUs. So the same configuration, the y-axis is now speed up over single Polaris node. So higher than 1 means faster than Polaris node, and lower than that is slower than Polaris node. So in this case, we use 4 A100 GPUs on Polaris and 4 MI250X GPUs on Frontier, which means HGCD, and 6 Intel Max GPUs on Aurora, which means 12 stacks of Aurora GPUs. Now, the node architecture is different. So we have 6 GPU card on Aurora, which is 50% more GPU than other system. So as a result, Aurora node perform best with the 10 applications, while still Frontier node operate better with one application, which is called the FlashX application. So that means FlashX is fully optimized on the Frontier node, and then there is some room for improvement on Aurora side, right? Okay, so this is a single node performance. If you have any question, you can just speak up. Okay. And then we did the weak scaling test. So that means we just scale out with up to 5% of the system. Go ahead.
Performance. So on the Intel GPUs. So what was the difference? That one seems to be like the biggest difference. Well, maybe SST, there's similarly large differences.
Yep.
Was there some particular characteristic of the PVC or just that the software?
So
Better.
what we have some discussion later about the framework, but what we observed was framework module is portable across the system. For example, this is PyTorch framework.
I see.
But that framework has a lot of knobs for the performance. So the stability versus performance, right? So in that case, we have some choices of for the best. Then, yeah, I think this is coming from framework module.
I see. So,
I guess, but we still need more further investigation.
So then it's possible that on the other GPUs with sort of similar tuning and effort that there's also a significant upside.
Yeah,
That's interesting.
That's true. Yeah.
Do you remember if Cosmic Tiger was using the concurrent compute streams?
I'm sorry.
Do you remember if Cosmic Tiger was using multiple
CCS mode?
Yeah.
I don't remember that. Do we have Khalid here? No. Yeah, so we tested the CCS mode with the FlashX and we got the 2x speed up, but I don't remember we did use same configuration for Cosmic Tiger or not.
Okay. Yeah,
that could be a reason, I guess. Yeah, if you use that. Yeah. Okay. So weak scaling, scale out up to 5% of the system on Frontier and Aurora, which means around 512 node, and 25% of the Polaris node, which is under 20 node. This is AML wind example. X-axis is number of node. So as we increase number of node, and the left axis shows the figure of merit. So you can see performance increase linearly here, right? So green with a solid marker represent the figure of merit of the NVIDIA Polaris node. Black with the solid markers is Frontier node, and blue is Aurora node. So as you can see from the node-based comparison, with AML wind, Aurora is slightly faster than Frontier, but they are same ballpark, and both of them are faster than the Polaris node. And you can see the efficiency drop on the right-hand side axis. You can see the parallel efficiency over the single node performance. And as you can expect, as we increase the number of nodes, we lose the efficiency, but we don't see any big difference between the efficiency drop between the three different systems, right? Next is a CNS sleep paranormal. For some reason, Frontier is slightly slower than Polaris, and Aurora is faster than Polaris. And if you look at the efficiency, Polaris efficiency is pretty high, maybe because of the low performance on a node. I'm not sure. We are not sure. We need more investigation. But on the Polaris side, Aurora side, we can see the performance drop stepwise. So kind of difference between the CNS and AML window application. Sim AI bench case, again, Aurora is faster than Frontier, Frontier is faster than Polaris. And Frontier and Aurora efficiency is pretty good. Most cases, it's very close to 100, but for some reason, Polaris lose efficiency. So our first guess is Polaris has a lower network bandwidth than the other nodes, so that could be the reason. But I think to identify the exact issue, we need more investigation. So I think HPC Toolkit or Tau can help us out to identify the issues. And cosmic tagger case, it's very similar to other case, but the interesting thing is Frontier case, it loses efficiency very, very quickly. This is not a fault of the Frontier, but we have some further discussion about what happened with the framing module. But simply, quickly we can say framing module has several different knobs to choose better stability and better performance. Cosmic tagger case, the most performed environment variables result in the very unstable results. So we need to go back to more stable knobs. And then it is why the Frontier case will lose efficiency very quickly. In the LAMS case, efficiency drop is pretty similar to each other. Aurora is faster than the other two systems. And XDC case, we use, even though we use two inputs within weak scaling, even though we use weak scaling, but we use two inputs for the small number of node and large number of node. And the efficiency changes pretty a lot, we see here, right? And then FlashX applications, efficiency drop is pretty similar to each other. You may need to remember this chart because FlashX application, we tested with a strong scaling and we see some different efficiency drops. So we can discuss what happened in this case, right? And Megatron deep speed, very similar. The interesting thing is on 512 node on Aurora, we have super linear efficiency, which is great number, but we are not very comfortable. Something is going on over there, so we need to dig into what's going on over there. And SST applications and OpenMC applications. So this is kind of the snapshot of each cases. And then with the games application, the WKMX application, we did a strong scaling test with the same number of nodes. Again, we use two different input, small input for up to 8 node and the large input for the more node. So here you can see some discontinuity at here, right? So we have small node, large node with games case and WKMX case and FlashX case. So do you remember what happened with the FlashX with the weak scaling? So efficiency drop is pretty similar to each other, right? But here we can definitely see Polaris efficiency is higher than Frontier efficiency, and Frontier efficiency is higher than Aurora efficiency, right? So the reason is Polaris has the smallest, the slowest GPU. So as we increase the number of nodes, the network versus compute intensity slowly increase, right? So less network bound than the other GPUs because GPU is slower. So with this reason, Frontier has more loss in the efficiency, but compared to Frontier and Aurora case, they have a similar speed of the GPUs card, but the Aurora has 2 more GPUs than the Frontier, right? So on the same number of node, we have a 50% more number of GPUs. That means we have more computing resource, so less occupancy. So as a result, we lose efficiency quicker on the Aurora side. So it looks bad, but in another way, we can think, oh, same number of nodes, we can solve a bigger problem on Aurora than the Frontier, and bigger problem on Frontier than Polaris, right? So depending on the configuration, you may enjoy the better performance on Aurora and Frontier. So that's kind of performance data, and we found several key concepts to get the better performance. So first thing was CPU GPU binding. Depending on the application, CPU GPU binding is very important. So for example, games application, they have an interesting setting in the MPI. So half of MPI is running computation, another half just in charge of the communication. So proper pairing between the computing MPI and the network MPI, communication MPI is very important to get the better performance. So proper binding, games case, we can get a 2.5x speed up without the proper binding. NWKMX is another interesting part. Somehow it's very sensitive to CPU NUMA effect. So you can see Aurora has a dual socket. So by the default, we just spread the MPI, not by the default, but the recommended way is we want to spread the MPI ranks across the two different sockets. But for some reason, NWKMX is better to run on the single socket of a CPU with a 6 GPU. So in that case, NWKMX we got the 2x speed up. And AMR Wind is less sensitive application. So without the default binding versus the proper CPU binding, we got around 5% speed up. This is a lot, but compared to 2.5x and 2x speed up, it's kind of relatively small, right? The another part is, of course, you have to have a proper GPU binding. So if you just don't manage GPU binding properly, you may oversubscribe your MPI rank on the same GPU tile or using implicit scaling. If that happens, AMR Wind case, it lose performance to drop to 25%. So GPU binding is pretty critical. The another part is for ML application, the core binding for one CCA worker is very important. In Cosmic Tiger case, by leaving separate CPU cores for one CCA worker, we could get around 10 to 15% performance gain. The another part is using the GPU or MPI. So this is a good way to remove the cost of staging GPU buffers in the host memory. So CNS case on Polaris, with GPU-aware MPI, you can see the solid line. But without GPU-aware MPI, even a single node case with four GPUs, it loses some performance because of in this case, performance bottleneck is using the GPU buffer in the host memory. So by using GPU-aware MPI, you can get the better performance. We could get the better performance in the Polaris case. And XGC with two input team compared with GPU or MPI without GPU or MPI. Every case is GPU or MPI is better than without GPU or MPI. But it's not a free lunch. It's available on the multiple system, but it's still, depending on the case, it's still some buggy. So in CNS case, we had with the some number of nodes, 120 nodes, I think. We got some errors with the improper initialization. So our application developer need to identify the bug and fix the problem. And also, we saw some memory issues with XDC on Polaris and some memory leak in the Aurora. I think those issues are resolved now, but what I want to say is this one possibly have some bug with some SDK update. You need to be aware of it. So this is a kind of comparison with ML. So ML uses a TensorFlow PyTorch framework, which is portable across the different system. In general, which is good shape, but depending on the architecture and application and workload, you may need to find some different environment variables. So on frontier side, the 512 node case, this environment variable we set the PHP, but we got some instability issue, which means a long execution, and then just exit timeouts just failed, right? So, and then the OSF suggested another environment variable, and then when we use that, we lose the efficiency very, very quickly. So it's kind of the issues. And then I think our team is still investigating this issue, what's going on over there. And also some another case is we have some setting for the number of leaks to RCCL collect library in this environment variable. But depending on the application, for example, Sim AI bench, we see on the 2048, the GPU case, we got 40% performance gain. But for the same configuration, the Cosmic Tiger is also very less sensitive to this environment variable. So what I want to say is you can use the framework module on different system. It's very, very easy to use, right? Just change some part of code. But once you do that, you may need to investigate your application is fully optimized with the several environment variable. And then, as Tim mentioned before, on Aurora side, there is some CCS mode, compute comment streamer mode, which is somewhat similar to MPS mode on the NVIDIA side. And with that option, with a FlashX application, with the same workload using the CCS mode, we could get around the 2x speed up. So yeah, that's our observation. And when you presented this one, we are asked to talk about performance portability, which is great. So we're kind of big fan of using qualitative performance portability assessment using the Panicook's approach. But in that case, this is a really good approach for some mini app or some simple benchmark. But in the application level, we found out several challenges. So it requires understanding of efficiency of implementation of each application on each architecture. Also, detailed assessment of the application interacting with some different components, right? So CPU, GPU, PCIe, and NICs, etc., right? And also, various kernels, they have different performance bottleneck. It's not easy to find out what is the most representative bottlenecks, right? So depending on workload, that ratio can keep changing. And also, additionally, you want to use the roofline model, great in general, but with the application, with the real workload case, due to the high overhead, another instability, it's very hard to with all the application across these different systems. So instead of doing the qualitative assessment, we want to do the quantitative assessment, a little bit easier, but we just want to get a snapshot of that based on the GPU door precision and HBM bandwidth. And according to Amdahl's law, if your runtime of door precision bound by the application is around 40%, that means your possible speed up is around 25%, right? It's kind of the ratio. So we just look at the figure of merit data across the different architecture, and 6 applications shows more than 25% performance gain on Polaris. And games and sim AI, Frontier Aurora performance is pretty similar to each other, so we can say qualitatively performance portable. Cosmic Tag SSDK is high on Aurora, which means on Frontier side, room for improvement. And RBKMX XCC higher on Frontier. That means on Aurora side, there's some room for improvement, right? So most of them shows some level of performance portability. No programming model or algorithm motif achieved the more performance portable than others. So maybe we just kept 12 MPI, right? 12 applications, maybe not too much data. So concluding, using the 12 applications, we try to evaluate the performance across different systems. We want to cover very wide range of the domains, and also different computational algorithm, different base language, different portability layers, and investigate the GPU-based, node-based, and scaling data. And we also discussed key issue and concept for the performance and some qualitative performance portability. But this is just based on figure of merit data, so we want to go deeper with tools to understand more characteristic. And also in the future, we want to include some I/O. I/O is another big part in the performance, right? And we also want to extend this work for the power usage as well to understand power efficiency. So, yep. We appreciate the support in AirSafe and WSF, and that's all.